Beautiful.
Great. So, good afternoon, everyone, and welcome to today's seminar. My name is Yanrong Xiao, and I am the chair of the USACM student chapter. I would like to thank you all for joining us. It is my pleasure to introduce today's speaker, Lara. Theo recently graduated from MIT with bachelor's degree in mathematics and physics. His research lies at the intersection of applied mathematics, computational mechanics, and biological systems with a particular focus on fluid structural interactions. Working with Professor Ken Carvin, he developed a fully Eulerian simulation method for modeling fractional contact between soft bodies immersed in a fluid. He has also worked with Professor Jan Dankel to study the swimming and feeding dynamics of jellyfish, examine how the vortices degenerate influence pre-capture and energetic efficiencies. This fall, Theo will begin his postgraduate studies at the University of Cambridge, where he will continue exploring applications of mathematics to biological systems. Please join me to welcome Theo, and I will mute myself. The screen is yours.
Lovely. Okay. Yeah. Thank you, Yenra. Good afternoon, everyone. This is some work I've done with Ken over the last three or so years. Working on these sort of contact-rich problems involving lots of contacting solids inside a flowing fluid. Ken was at MIT, but he is now over at UC Berkeley in the mechanical engineering department. Cool. Let's do this. So first of all, fluid structure modeling is tricky to do by nature. That is because we tend to model fluids and solids in very different ways. When we model a solid, we will use a reference frame that moves with the material. Usually take your mesh nodes to correspond to actual points on your material, and you have this deforming reference frame, which is sort of a natural application for elasticity problems that are relevant for solid mechanics. But for fluids, instead of having a moving reference frame, you tend to have a fixed reference frame in space, where the fluid flows through this fixed mesh, which is more natural to simulate things like the continuity equation and the momentum balance equation that are needed for fluid simulations. So the question is how do we combine this sort of moving reference frame in the solid domain with the fixed reference frame of the fluid domain to model both fluids and solids at the same time? This question is not new, luckily for us. People have been doing FSI simulations for a few decades now, and there are three primary approaches. Firstly, you can treat both the fluid and the solid as completely Lagrangian, right? Where you discretize them on a deforming mesh and you have a coupling at the shared interface. This is good for very accurate tracking of your fluid-solid interface, but it is tricky since you have to deal with constant remeshing and can be tricky to deal with very highly moving fluids. And then the most popular approach are these mixed Eulerian Lagrangian approaches. Think of something like the immersed boundary method, where you have the fluid solved on a completely fixed grid, and your solid is represented with a deforming mesh, and you have coupling between the fluid and the solid via force interpolation. This is good for large fluid domains and very complex flows, since you're simulating the fluid on this completely fixed grid. But it can be hard to do your interpolation between your fluid and your solid. You have to be very careful about how you handle this boundary. And then the technique I'll be addressing today are these fully Eulerian approaches, where you have both the fluid and the solid represented on the same fixed grid. There is no explicit boundary between the two domains, only some implicit representation. So why are we interested in these Eulerian FSI simulations? Well, there are a few benefits for us. First of all, there is a single unified velocity field, right? There's no need to keep track of a separate velocity for the solid and separate velocity for the fluid. There's also no need to do remeshing. You can very easily do large solid deformations. It is, for that reason, very straightforward, easy to implement, I mean, relatively easy, right? And it is sort of naturally parallelizable. You can do lots of fun computational tricks with adaptive mesh refinement. You can do domain decomposition just to accelerate all your simulations. And there are also a few trade-offs that are relevant. First of all, like I mentioned, there is this diffuse fluid-solid interface, right? Instead of having a sharp fluid-solid boundary, your interface is smeared over several grid cells, right? So you don't have this sharp resolution. meaning that the interface size can actually impact the physics here. If we look here on the two images to the right, the top one has a slightly smaller interface than the bottom one. You can see that the results are the same, but there are sort of non-negligible changes due to this change in the interface size. You have to be careful about how you treat the actual fluid-solid interface in these simulations. And then more importantly is how do we actually keep track of the position of our solid, right? The solid strain and stress depend on its deformation over time. And that deformation, the Lagrangian-like history, is not something we naturally capture in our Eulerian field. That second question was resolved by Ken Cameron and Chris Rycroft back in 2012 with something called the reference map technique. The idea being is that we are interested in this map from the original configuration at time equals 0 to the deformed configuration at a later time. However, that map is not something we track on an Eulerian domain because although these points may start on our fixed reference grid, they will not naturally evolve to our fixed reference grid at a later time. What does exist always on our fixed reference grid is the backwards reference map, which moves us from the deformed configuration at time equals t to the undeformed configuration at the original time. And then all we have to do is we can just invert this reference map to find the deformation gradient, which is the variable relevant for calculating things like the solid stress. It is not too difficult to convince yourself that this reference map is just affected forward in time with the velocity field, such that as we know the velocity v, we can just update the reference map, and then we just update the deformation gradient each time step. And this allows us to track the solid history-dependent stress on our fully Eulerian mesh. So in sort of 5 simple steps, the RMT reference map technique algorithm, we first solve for the deformation gradient by inverting the reference map. We assemble the fluid and the solid stress tensors. For the fluid, we can use a Newtonian stress. For the solid, this is just a Neo-Hookean deviatoric stress. Then we just evolve the velocity field forward in time. There's a single velocity field everywhere in the simulation domain, and we just have a different stress tensor depending if we are in the fluid domain or the solid domain. After that, we just enforce incompressibility via your favorite projection, and just advect the reference map forward in time using this new velocity field, rinse, and repeat. Now, these sort of 3 bottom steps is your just standard incompressible Navier-Stokes solver, and just add on this reference map paired with the solid stress to incorporate solids into our simulation. One thing I haven't mentioned yet is the actual fluid-solid interface. There are a few ways people go about doing this. We tend to take the most flat-footed, straightforward approach, which is using a level set field. This level set field tracks the distance to the nearest solid boundary, right? So it is 0 at the fluid-solid interface, larger than 0 in the fluid domain, smaller than 0 in the solid domain. And from this, we are able to identify what parts of the simulation are solid and what parts of the simulation are fluid. Instead of advecting the level set field forward in time, we can just reconstruct it from the reference map, which already exists, which ends up being a little bit more efficient. There is this transition zone, this small region where this level set field is smaller than some small epsilon. And in this region, it is slightly viscoelastic since the solid and the fluid are sort of smoothly blending into each other. So a few fun examples. This is a strained disk released within a fluid. The initial sort of stretching of the disk causes a negative pressure inside the body. It is then released and is dampened over time to come to rest due to interactions with the viscous fluid. This is, again, all done on an Eulerian simulation, right? There's just one computational mesh, and the solid is represented using this level set field that I mentioned. Then a more fun example are these flapping flags. These are pretty cool. There is a little sort of flag, if you will, with one end fixed in space, the other end free to oscillate. These are placed in a constant horizontal flow. The wake behavior of these flags causes either flapping motion, unstable motion, or sort of non-existent motion in some cases. The sort of thin flag is something you can resolve more or less analytically, but this thick flag, where the actual elastic properties of the flag matter and are a lot more relevant, are harder to approach analytically. And it's sort of the perfect problem for these sorts of simulations, right? Where you have a solid whose elastic properties matter in the overall physics. So these are some pretty cool examples done back in 2020 by Chris Rycroft. And just for fun, you can do a simulation sweep for your thin flag and find very good agreement with the actual analytic result. So this black line is the analytic stability ratio, and you have some decent agreement of your stable and unstable regimes for your flapping flag. So I thought that was kind of neat. Now, the sort of another advantage of this Wallerian technique is solid body contact. So this is what I'm going to focus on more or less today. In that, because you simulate all your solids with this level set field, it is very easy to do contacts between two approaching solids. If instead your solids are represented as a sort of mesh or series of points, you would have to look over each point, looking at each other point, and that just becomes a expensive and complicated operation. But here, all we have to do is just combine the level set function of both solids. Okay, sorry about that. You have your two solids, phi1 and phi2. You take the difference of these two solids to have this sign interface distance function, this phi1, 2, which just tells me how far away the solids are from each other. And using this sort of field, this again is a field defined everywhere in our domain. We can construct a repulsion force or a stress field, right? This force just becomes larger when the solids are closer together and becomes smaller as the solids separate. And this contact does not at all depend on the fluid. Remember, there is a fluid between the solids, but you have forces that exist entirely within the solid domain. So a few fun examples. These are some sedimenting bodies, right? Over here we have some squares on the left, which are coming into collision and interacting with the surrounding fluid. All of these contacts are built from the pairwise phi1, 2 fields. And on the right here, we have several of these spindly noodles with different densities, again, settling under the influence of gravity. Again, all these contacts are built with our pairwise interaction scheme. This is all well and good, but there are two sort of primary limitations to this more, I'll call it a naive contact implementation. The first of which is that you need a different level set field for each of these bodies, right? Each of these squares has a different level set field. And for contact, each body looks at each other body to build its phi1, 2 interaction field, right? And that is sort of an n squared operation for n bodies as you look from each body to each other body. And the sort of second thing is perhaps not immediately obvious. There is no solid body self contact, right? Look here on the right, all these noodles, they squirm and they touch each other, but they never quite bend enough to touch themselves. So our question last year was how can we address these solid body self contacts? It's a more interesting class of collisions in this fluid immersed domain. A self contact is tricky to do, primarily because you only have a single level set field, right? When you have a single solid body, right? So this little U shape is coming into contact with itself. One side of this U has no way to sort of see the other side of the U because the level set field does not provide any information about the location of the other side of the U shape, right? So it has no way to naturally detect when a self contact is occurring as opposed to a two-body contact with two different level set fields. There is no second object here to define your sign distance function. And the whole problem with these self contacts, apart from, solid self penetration, which is unphysical, also when that happens, your reference map becomes non-invertible, and that means your simulation crashes and you are sad. So also a bad thing to have happen. To resolve these self contacts, we create an auxiliary stress field. This is a little bit of a complicated procedure, but essentially you can dream up this level set, this psi field, which is a secondary field, providing as a contact auxiliary field. Up here on the left, this is just the level set field, and the psi field becomes largest in the contact region. Right, so right here in the middle of our U shape is where we need the actual repulsion forces to activate. The psi field is built via an integral kernel of the local level set gradients, right? So it grows when the two sides of the object are coming into contact. From this psi field, you can build yourself a self-contact stress tensor, which acts in the direction normal to the solid surface. And then you have a contact force, which is the divergence of this stress, right? And you have this divergence just so you can ensure continuous momentum conservation in your contact, right? You need momentum conserving contacts such that when the U shape touches itself, it doesn't just go off in some direction. Here on the bottom right, these are the resulting self-contact forces. As you can see, they are pointed away from the collision zone, and they're also equal and opposite in magnitude, which is what we expect. So with that being said, we can do something interesting in that we have not only resolved the self-contact, but we've also resolved the second problem of our contacts. We can treat all contacts as quote unquote self-contacts by representing all objects with a single level set field. So in this way, all contacts are treated in the same fashion, and you just have a contact force, which is an additional Illyrian field, which is carried out throughout your simulation. And you no longer need this pairwise contact detection between your n different objects. All you have to do is just treat everything with the same level set field. So all contacts are effectively cell contacts, and there's no longer this n squared scaling for your n bodies. So here is a fun little example of a sedimenting spindly noodle and several disks. The disks and the noodle come into contact in several places, and the noodle also comes into contact with itself. And all these contacts are treated in the same way as the bodies eventually settle under the influence of gravity. I will come back to contacts in 1 second. One other thing I want to talk about is locomotion and actuated bodies. This is another benefit of our technique in that actuation is really simple to do. You just add a time-dependent active stress to the solid body, right? So the stress just enters momentum balance like the existing fluid, elastic, and contact stress tensors without any extra work done on your end. This is a simple quote-unquote lamprey that swims along due to the actuation inside its body, right? We haven't yet extended this to more realistic applications, but you can sort of easily imagine you have muscular dissipation, sort of neuromuscular signaling. You already have a map of the You already have the reference map, which tells you the points within this object. So you could, pair those up to neurons, for example, and have that couple into some sort of model for your muscles in some biophysical application. And then just to have a lot of fun, you can combine this actuation with all of our contacts. So all of the bodies modeled are modeled with a single level set field. All the contacts, the multi-body contacts and the self-contacts are treated in the same fashion. And this is all on a fully Illyrian simulation domain. Again, these are not meant to be very realistic. I gave them funny names for that reason. On the left here, we have these quote-unquote fat eels, which are squirming rectangles which crash into each other. We have these confused lampreys, which are wildly oscillating and moving into each other, and these floppy flagella, which are just discs with spindly appendages, again, flopping about and touching each other. These shapes are chosen fairly arbitrarily. You can do any shape you like, really, as long as you can represent it with a level set field. You can also describe any actuation you desire. So these are just fun little examples of what we can do with our method. Now, a more recent extension of this contact work has to do with frictional contact. This is something we started thinking about last year, in that the contact between two bodies will generally not only have a normal component keeping the bodies from touching each other, but also a tangential component, right, preventing sliding and causing the bodies to stick together. And that is called friction. So can we add friction to our contact model for this reference map technique? This is, again, tricky to do for two reasons. First of all, you have no notion of the velocity of an object, right? A frictional contact depends on the velocities of the objects that are coming into contact, right? With two sliding bodies, your friction force will depend on the relative velocity between these sliding bodies. So you need to be able to identify this relative velocity field in your Illyrian sense when you just have a grid with your global velocity field, right? You have to separate both sides and identify a relative velocity field between these two tangentially sliding sides. And then you also need to develop a frictional rheology that develops the Coulombic friction behavior. So the friction force should be less than or equal to this coefficient of friction times the contact force, reproducing both the sticking regime and the sliding regime for your frictional contacts. On the first of these points, is relative velocity is tricky, again, to do, but we do something similar than what we did with the auxiliary field psi to detect contacts. The relative velocity is computed by averaging across the fluid interface. So if you have two objects that are tangentially shearing, or two parts of the same object, again, it is all the same in our formulation. You are interested in the relative velocity between these two objects. You can just pick one object, look across in the normal direction, and average among points that are near the interface of the other object. That gives you a quote unquote opposing velocity of the opposite object. You do the same procedure reflectively on the other side to obtain the velocity of the first object. Find the difference to give you a relative velocity field constructed via this averaging procedure between your two bodies. So it is sort of a bulk construction from the global velocity field, right? And we are assuming that there are many, many more grid points in the actual size of these objects, such that this sort of bulk average velocity is representative of the global velocity of these moving objects. And importantly, this relative velocity construction is reflexive, right? So each side obtains the same relative velocity. Give a minus sign such that your forces, which scale with this velocity, are actually reflexive as well. And then once you have this relative velocity field, you can construct a frictional contact rheology. We use a spring slider dashpot rheology, right, inspired by the motion of granular medium and Ken's work modeling granular medium. There is an elastic contribution to the frictional forces, right? This spring builds force proportional to the relative displacement between our two sliding bodies. And this allows the two bodies to stick together and stay sticking together due to frictional interactions. There's also a viscous contribution, which scales with the relative tangential velocity. And this is what dissipates energy away from the contact, allowing two shearing objects to relax in the absence of external forces. And then there's this slider contribution, which just caps the friction forces below the Coulombic threshold, which is important for our model. And all your forces are applied at the contact interface between the fluid and the solid. So now that we have friction, we can return to our examples. This here is back to the little U shape, but instead of just coming into self-contact, the arms of the U are also tangentially shearing against one another. And this shearing causes frictional forces to exist on the interface of the U shape. If you notice, these frictional forces are always pointed in the direction of opposing motion, which is the direction they should be, and they're also equal and opposite. If we make a little loop here in displacement force space, there's a closed periodic loop during this periodic horizontal displacement, indicating that we are indeed dissipating energy. There is mechanical work being done by our frictional forces. The ratio of the friction and the normal forces also saturate at the Coulomb threshold of the coefficient of friction, in this case is 0.5. So it is satisfying Coulomb's law, which is what we want for our frictional law. A second example, this is a little block sliding on a ramp, back to whatever the first physics class you ever took. This block at a certain angle will begin to slide down the ramp. Same thing here, we just have this horizontal forcing, which slowly increases over time. When there is less horizontal force than the normal force times the coefficient of friction, so in this regime from time equals 0 to time equals 180, the block stays in place and doesn't move, right? This is the sticking regime where there is enough friction force to keep the block from slipping down the ramp. But as soon as the slider yields and there is more horizontal force, then there is friction force keeping the block in place, the block begins to accelerate down the ramp. So we have this very qualitative stick to slip bifurcation, and the actual acceleration of the block does match our analytic expectation, meaning that the magnitude of our friction forces are what we expected them to be. And this stick-slip behavior is only possible because we have both the dashpot and the spring in our friction model, right? We need the spring in order for the block to stay in place, and we need the dashpot in order for the block to accelerate with this characteristic velocity. And then this is an example of a curved interface. We wanted to test not only a parallel contact between two bodies, but also a rotating contact in a quote unquote ball bearing configuration. So there's a little disc sat within a hoop that is rotating. The shear between the two objects creates a frictional force preventing rotation. And we want to test two things here. We want to test the normal force balance such that both the hoop and the disc have the same amount of normal force. There's force balance there. And there also should be a torque balance in the torque exerted by the frictional forces on the hoop and the disc. Those should also balance, right? Our friction should not add any net torque. And indeed, as we refine our grid, we observe first order convergence towards both the normal force agreement and the torque agreement, right? So we have normal and tangential force balance. We have convergence as we would expect for these shearing curved interfaces. One final analytic test is a convergence to this Hertz-Mindlin disk shearing test. So we have two disks in space that are pressed together vertically and then sheared horizontally. There is an analytic solution for the normal and tangential components of the traction in the case of small deformations. And indeed, as we refine our grid study, right, we have the same simulation modeled on many different grid spacings. We observe convergence to this analytic distribution for both the normal components and the tangential components of the traction distributions, right? So this validates our contact, it's consistent with what we would expect analytically. And then just a fun example. This is, oh dear, what has happened? There we go. This is a little U shape sandwiched between two rods. And the rods begin to, or the top rod begins to slide back and forth. The frictional contact between the U shape and the top rod causes the U to sort of translate and also rotate in space. So this is an example with self-contact, right? You can see the U shape touching itself. There is multi-body contact of the U and these rods. There's, obviously a fluid that is interacting with both of these objects. And all of these contacts are also frictional, causing the U to move around and become displaced, right? If it weren't for friction, the U would just stay in place since there's no tangential component to the forces between the rod and the little U shape. So this is a fun example of these multiple frictional contacting bodies. And then one final test case. This is our sedimenting bodies with and without friction. So back to the example I showed you with these little accordion shapes and the 6 discs. Same material parameters, same initial conditions, same gravity, same everything, except that in the case to the right, there is friction compared to the case to the left when there is not friction. And this addition of friction produces sort of qualitatively different sedimentation over time and a different final resting state. Again, there is self-contacts, multi-body contacts, all of them having friction. And in the case of friction, we just have, noticeably different physics than the case that without friction. So that's another fun test case to do with these friction models. So conclusions. We have developed a method for solid body self-contact, right? Extending the Illyrian reference map technique to be able to handle solid body self-contact. Using this self-contact model, we unify a contact framework to handle all bodies with a single level set field, right, which improves these collision simulations, especially for the case of many contacting bodies. And then we decided to add friction to our contacts, right, extending our model to reproduce the sticking, slipping, and sliding behaviors of contacting bodies. And we benchmark our frictional model against several test cases and convergence studies. A few fun papers, if you're interested in reading more, there's this 2012 paper on the reference maps, 2020 paper. There's two sort of seminal papers on the reference map technique. our work on this self-contact is this paper in 2025. And then there's a friction paper that is, hopefully coming soon. The recording of this will be on YouTube somewhere, so you can look at these papers at your own leisure. And then one final thing, future work and things we are looking to do in later on. The most obvious thing is 3D. We already have a 3D code for the reference map technique, developed by Chris Rycroft and Nick Durr back in 2024. Everything we talked about today with our contact model and our friction is fully extendable to 3 dimensions. So we can add these friction contacts and these self contacts in 3D. We have this dream of doing this rope and tying this rope, like creating a knot in 3 dimensions. I think that would be super neat. Also, very recently, Sun and Rycroft developed a reference map technique application for the last Boltzmann method. We can again try adding friction and contacts to this method. It is favorable for our parallelization and faster computing. And then related to that, we could have adaptive mesh refinement, multigridding in our Illyrian scheme. You can imagine a problem where the contact is very localized between one small part of two bodies or the same body. And by having, adaptive mesh refinement, we could focus computational effort on that small bit and accelerate the rest of the simulation. And then the last idea we have just on the back of a napkin, cracking and breaking and fracture, right? We could think about what happens if an object sort of cracks and separates into multiple bodies. We already have the reference map technique and we already have a good model for contact. So that could be a natural extension to add more physics to our simulations. That is everything from me. Thank you very much. I hope you learned something, and I can now take your questions.
Thank you so much for your great talk. Everything's explained in super neat ways, and I really like the way how you show those equations. It's
Thank you.
very clear to me. And I have one very important question. Does the examples you shows have some open source code?
Oh, yes, it does. It's all on GitHub. If you just Google Chris Rycroft reference map technique, there's a GitHub page with all this code. There's also an addition for the frictional contacts and the self contacts there. So you can play around as much as you like.
Yeah, sounds great and very helpful. And I also have another question. Would it be very challenging if we also want to implement the temperature field into this problem?
Oh, a temperature field. I hadn't thought of that. Yeah, you could have, solid bodies whose properties depend on the temperature.
Mm.
You can do some sort of temperature equation modeled on your same fluid domain. You already keep track of the location deformation of your solid, so just add on sort of temperature dependent solid properties. So I don't think it would be too difficult to do either because you already have all of this framework telling you where the solids are, where the fluid is. You just solve a heat equation at the same time.
Yeah, sounds great. And I think it could be extended to many complicated problems.
Mhm.
And we also have some general questions for the audience. If you have any questions, feel free to break in and directly ask. So I would like to ask, would this framework could also be extended to more realistic software material behavior, such like viscoelasticities, anisotropy, or the other mechanical response of the biological tissues?
Generally, yes. Very likely, yes. The sort of reference map technique, it already separates the sort of kinematics from the constitutive law that is happening, right? All you have to do is just plug in your new Hookean stress back in one of these equations here. Yeah, way back here. You just plugged in your stress strain relationship. So you can just imagine doing that with a different relationship, right? All you need is this deformation gradient. So you could, model a viscoelastic solid or a plastic solid. or some solid with, material dependent properties like I mentioned previously. So in principle, yes, I'm sure there are complications that may arise, but because you have this nice separation from the actual deformation gradient from the stress tensor that's going on, you should be able to do whatever solid properties you're interested in doing.
Yes, I agree with that. I think, yeah, it is very likely to implement those things inside. And
Yeah.
so far, you developed a lot of things. What do you think is the most challenging part with this project?
The most challenging part about this project, these little graphs I show of the convergence studies. They look very simple. You have, your 9 points and they converge very nicely, but I'm sure as you all know, these are a pain to actually get to. A lot of these cases, especially this sort of disk shearing case, tends to be very finicky. And you also have to be careful of how long these simulations take because our code is extremely non-optimized at the moment. So some of these simulations take, several weeks, and if you mess something up, you have to wait several weeks to try again. So every convergence study you do is generally tricky, but the convergence studies are, very important, just so you know that everything is working like it should be working. You actually trust your results for more complicated cases.
Yeah, exactly. Do you run them on the cluster?
Sorry?
Do you run those simulations on the high performance computer
Yeah.
clusters?
So we
Yeah.
run it all on a cluster, but the code is just not optimized right now. When
Yeah,
neither
exactly.
me or Ken are very good with computers. We have code that works, but doesn't work very quickly.
Yeah, it's especially for those many body problems. Yeah, it
Yeah, for
costs a
sure.
lot of computation expense, and it is always
Mhm.
a very difficult problem in the computation mechanics.
Yeah, it's always.
Yeah, so you work with those great professors, Ken Cambrins and Jan Dunkels. How do they shape your research interest and influence the way you approach scientific problems?
Oh, sure. Um, I mean, I don't think that fluid-solid interaction problems is something that anyone really uh, thinks they're going to be doing when they go into undergrad. But
Yeah, I was also very impressive, like how far you go as a undergrad.
no, I think it's a really fascinating class of problem because it's the type of problem where you can make progress just by like thinking really hard. You don't necessarily have to be use very sort of advanced analytic techniques or advanced computational techniques. It's just about knowing the physics and thinking about models that can replicate this physics and trying to implement those models. That is sort of what I enjoy about these areas of research. And, more so in the work I've done with Professor Dunkel and Professor Cameron, but you can also model biological systems, right? I love these little swimmy flavors. It's not something we've done yet, but in my other work, we have been able to compare these simulation data with actual experimental data for swimming jellyfish. And you can imagine doing something similar, which I think is super neat, right? As someone who despises experiments and will never go into a laboratory, it's fun that we have these simulations that we can compare with experimental results and hopefully apply to actual sort of real world applications. Yeah.
Yes, and I really think it is very close to the real world applications.
Yeah, you can imagine this being a fish or a jellyfish or some other, bacteria or flagella moving around, right?
Yes, all like the cells.
Yeah, so something like that, exactly.
Yes. So as a student who recently graduated, so what advice would you like to give to some undergraduate student who is interested in those interdisciplinary research at the intersections of mathematics, physics, computation, and biology?
Sure. I would say just do something you find fascinating, something fun, which is, generic advice, but once you find a research project that you enjoy doing and is fun to do, it no longer feels like work, and it's just a fun problem that you're exploring, and you get to make fun videos. I mean, I don't have, the strongest mathematical background or computational background, but I found a problem that was fun. I got very interested in that problem and I developed some, interesting results. It's also important to find very good mentors for you. I was very fortunate to find professors that were, very invested in my work and I could, talk to very easily. And better these mentors are, the more work you will be able to do and the sort of happier you will be while doing this research. So, just find fun and find great people to do that work with.
Yes, so thank you so much. And now I can feel you also become a people that doing the fun research and you enjoy your works. And I think you can also work in the futures with even more interesting projects. And all the
Yes, I
best
hope.
for your upcoming graduate life.
Thank you. Thank you.
Hope we have the chance to meet each other in the future conference.
Mhm. Yeah, it would be exciting.
So if our audience has no more questions, we will end today's seminars now. And Valerie, you can stop the recording.